Now, if you found the last segment interesting, this one is going to absolutely blow your mind, all right? And if you didn't find the last segment interesting, I think this is still going to blow your mind, okay? I know it does mine to this day. Let's just review what we learned here about our vectors and the operation that matrices have on them. So remember that a square matrix is a linear operator, which means it's a function, and it goes from Rn to Rn. So this notation we haven't used a whole lot, but this basically means a vector of n real numbers. That's what R to the n means. Remember, this funny looking R means the set of real numbers. So the domain for the function is the set of real numbers, or the set of vectors of real numbers of length n, and the codomain of the function is also the same. Okay, so that's why it's a linear operator, because it goes from the same set to the same set. We remember that if you plug in just any old random vector, the matrix's properties just are not revealed at all, right? It just looks like you just get some other vector back, and there's nothing that tells you anything meaningful about it. I have seemingly in parentheses there, kind of tantalizingly, because in this segment you're going to start to see, oh my gosh, it's not random after all. It's actually doing something really deep and really neat, okay? Third thing we learned was that there are certain special vectors, and there aren't many of them, but there are certain special vectors for any matrix where if you multiply the matrix by them, you get back the same vector, except it might be scaled, okay? But it's going to be pointing in exactly the same direction. And you may remember I said that if you have an n by n matrix, there's only going to be n of these special vectors, these eigenvectors here. And the amount that the vector is scaled is simply called the eigenvalue of that eigenvector. So every eigenvector has a corresponding eigenvalue that says, if you multiply the matrix times this eigenvector, you are going to get back an exact duplicate of it, except scaled by this amount. All right? And then lastly, we had this little bit of nomenclature called the dominant eigenvector. That's simply the eigenvector with the highest eigenvalue. Now, the purpose of this lesson is to talk about just how dominant the dominant eigenvector is. And this is going to blow your mind. Dominant is a very well-placed term, right? Remember that for this matrix, we had two eigenvectors. We had -1, 1/2, okay? So anything along that line, and I'm going to draw that line for us in a minute, was an eigenvector with eigenvalue lambda equals 2, and the other one was 4, 4. Everything in that direction got squished by the properties of the matrix. So if you multiply anything in the -1, 1/2 direction by this matrix, it will stretch it. It will double the size of the vector. If you multiply this matrix by any vector in the 4, 4 direction, which is exactly southwest to northeast, it will get shrunk in half, okay? And obviously, the dominant eigenvector is -1, 1/2, right? So here's what this looks like on a graph, okay? So I've plotted here in a dotted line the dominant eigenvector. And you can convince yourself that if you go -1, 1/2, because that's what the vector is, that you're going to get stuff on this line, right? So remember, any vector on this line is an eigenvector. And when you multiply that matrix by it, it's going to double, okay? Now, check this out. I'm, again, like we did last time, going to pick just sort of a random vector. Let's pick that one, 1, 2.5. And I'm going to multiply the matrix by that to see what its operation is, okay? So we did that last time, but you're going to see now when we follow through what happens. So remember, it takes the blue thing and it converts it to the red thing, and we didn't see any pattern or rhyme or reason there, right? Just looks like you give it one random thing, gives back another random thing, all right? So now we're going to complete the operation here. We're going to take this red thing and shove it back into the function. We're going to multiply it by that same matrix M and see where it goes. And it goes to -3.4, 2.4. Now, can you see what we're zooming in on here? Take the -3.4, 2.4, put that back in the matrix. Boom. Yep, you guessed it. This seemingly random vector, if you keep multiplying the matrix by it, it gets pulled inexorably towards the dominant eigenvector. Oh, deep. And guess what? 1, 2.5, that isn't special at all. In fact, this happens with every vector. Let's try this one, -2, -1. If I multiply that by the matrix, I get -2, 0. We did this example last time. But then let's again feed that into the matrix, and we get negative 2.9.9. Feed it in again, negative 5.4, 2.4. As you can tell visually, this thing is getting sucked to the dominant eigenvector. Just like a magnet, it is getting drawn to it. Let's try this one, negative 1, negative 2. Instead of negative 2, negative 1. Multiply by it. Oh, it goes that way. Again, goes that way. Again, goes that way. And also converging to the dominant eigenvector. Let's try this one, 1.8.4. Picked a random vector out of a hat. Goes to there, goes to there, goes to there. Dominant eigenvector indeed. And you remember what I said with the swing, the playground swing, right? I said the swing wants to swing at a certain pace. That's why it resists every other possible frequency you can throw at it. If you try to swing faster, it doesn't work. Try to swing slower, it doesn't work. The swing wants to go at exactly this many cycles per second. Doesn't matter how hard you hit the guitar string, piano string, how hard you blow your trombone or whatever. All the frequencies are going to get damped out except the one it wants to. Now, want, that's a pretty, mysterious word, right? That conjures up sentience and volition, right? Sort of sounds like, wow, this matrix is like, an intelligent entity. It wants to bring things to a certain thing. Obviously, it's not intelligent, but nevertheless, the action of the matrix on any vector at all, with one exception, come back to that in a second, the action of this matrix on any vector at all is to pull it towards the eigenvector. Now, the reason that's so important is because a lot of things that we use matrices for have to do with repeated multiplication of stuff, okay? So for instance, remember the Leslie matrix that we talked about in episode 7, right? That was to keep track of the population of bunny rabbits or whatever. And we could basically specify with a state vector how many baby bunny rabbits, how many 1-year-old, 2-year-old, 3-year-olds, or whatever the example was, right? There were in a particular year. And then we multiplied that by the Leslie matrix to get the populations for the next year. And then if we multiply it by the matrix again, we'll get the populations for the next year. And if we multiply it by the matrix again, we'll get the populations for the next year, etc., etc. So you see the pattern. We're again taking a matrix and repeatedly multiplying a vector by it, okay? Now, I mentioned that there was one exception. So let's talk about that for a second. You may have been thinking, wait a minute, there's another eigenvector. It's not the dominant one, but I remember this 4, 4 thing, and I remember that when you multiplied the matrix by it, you did not get it being pulled anywhere. Instead, it just halved it each time, H-A-L-V-E-D, right? It cut it in half every time. So what does that look like? Well, if we start in exactly the direction 4, 4, and I do mean exactly, I'm going to come back to that in a second, then if you multiply the matrix by it, yep, it's cut in half. And if you multiply that by the matrix again, yep, it's cut in half. And do it again, yep, cut in half, okay? So if you feed a vector to the matrix, which is exactly on the line of one of its other eigenvectors, that turns out to be the only case in which it is not going to be drawn like a magnet to the dominant eigenvector. But what if we change this just a little bit, all right? So look at this 4, 4 here, right? I'm going to change that, just scooch it over just to there, 4.1, 4. Now, what happens if we multiply this thing by the matrix, okay? Does it get cut in half? And does it point in the same direction? Well, kind of. That is kind of cut in half, and it is pointing almost in the same direction. Try it again. Is that cut in half and pulled in the same direction again? Yeah, sorta, kinda. But you can see what's happening here, right? That dominant eigenvector is dominant indeed. And if you do it again, it goes there, and now it's off to the races, man. Boom, boom, boom. Okay? Dominant eigenvector indeed. So no matter what vector you give to a matrix, unless it happens to be exactly one of the non-dominant eigenvectors, it is going to be pulled to the dominant eigenvector, and that is going to set up a lot of stuff. So if anybody ever asks me, hey, here's a matrix, kind of give me an overview here. What does this matrix do? Like I wanted to do for the f of x thing, right? And I could figure out what that function did. I don't look at all the numbers. I say, what's the dominant eigenvector, man? Because I can tell you right now, that is what this matrix is going to tend to do if you multiply it by stuff. It's going to take whatever vector you feed it into, and it's going to steer it towards the vector that it wants to go to. And that has immense repercussions because, as we're going to be seeing, there's a lot of places where that seemingly weird operation of repeatedly multiplying by a matrix is exactly what we want to do. And we'll see that in coming segments.